Yeah. And it is time for our another speaker series. And this title is Big Data. And Big Data is really hot topic. Of course, I now really know. You will know. Okay. Jeff is expert in the big data, and Jeff wrote more than 10 books. Has written 10 books. Okay, it's about the big data or big data related. It's expert. And also, Jeff has a master's degree from Washington University. Jeff won a Society for Actuarial some competition. And Jeff currently is a PhD student. And Jeff tells us learning is a life learning. Is that right? So now let's welcome Jeff.
My presentation today is big data and how to deal with it. I am, speaking of hot topic buzzwords, I'm a data scientist, so you may have heard of data science. That's another topic. So data science is a frequent user of big data. So that's how I've gotten somewhat involved with the big data field, is basically just dealing with the type of analytics that I need to do on data when it's in a very large size. Just to introduce myself, the current, I've been writing books since the mid-90s, but the current one that I'm working on is just artificial intelligence for humans, which is currently 3 volumes. The third one's in the works right now. So that is, artificial intelligence has always been kind of a passion of mine, and that's what I'm currently working on for my dissertation for the PhD. All right, what exactly is big data? This is a word that you hear thrown around a lot in the media. Big data essentially is any amount of data where it's difficult to deal with. So just as the analysis capture all of these things, just dealing with that size of data, is it difficult to deal with? Does it have its own unique set of challenges? Because the bigger the data is, the more there are challenges. If you're Google, where your goal is basically to download the entire internet so that you can search it and archive it and that sort of thing, then you're dealing with a very large set of data, and you need to work with that. So the growth of data. Basically, there are several thresholds of when does data become big. So if you're working with something like R or SAS or Python or some of these other common tools that you use as a data scientist or as an analytics person, the first threshold you'll deal with big data is the computer's RAM limit. So you give it your data set, you load it in, and it says out of memory. Okay, now you kind of got a problem. And there's several ways you can deal with that. The most obvious is just sample it. Don't use the entire data, but sometimes you do want to do that. And then there's other approaches for that. The next threshold is your fixed storage. This is the one where most people run into it. When you can no longer buy a hard drive on Amazon.com that is big enough to hold your data, and you want to move it just from one computer to another. Now, companies like at RGA, we have something called a SAN, Storage Area Network. So we've got hierarchies of hard drives, really fast ones at top, really slow ones at the bottom, solid state at the top, spinning at the bottom. And we can put really large data sets in there because they're all connected together using RAID technology that lets them. But the problem is, if you want to take that off of that computer system and now move it into another one, if it doesn't fit physically on a hard drive that you would plug into it, and those are up to around, I guess, 4 or 5 terabytes right now. If it does not fit onto that, now you've entered one threshold of big data, because it's, how do I even move this? How do I back this up? And that's a problem you run into as well. It takes a while to archive that data, to get it on and off. So often we will run experiments where we will damage the data set in the process, and now we've got to reload the whole thing. So that's, especially on the expensive SAN, that's how you make the IT department really happy with you and say, okay, yeah, I know the data set's 10 terabytes, but I'd like to take about 3 checkpoints of this along the way, and I need you to be able to restore that back. So that was the first threshold where I really ran into it, where just archiving and moving the data set was difficult. And we're talking sometimes 5-6 hours just to restore it. So this is not something you want to be doing several times in a day. And then another area where you tend to run into it, we'll see this when I get to the slide for it, but algorithms don't just scale linearly. So you can very quickly exhaust your algorithm and run into some serious processing time. So I remember not that long ago that I didn't even hear of the word terabyte all that much. Now I can go to Amazon.com and buy one. But there's also petabyte and exabyte and even zettabyte. So in the world of big data, you'll often hear in terms of how big is the data, they'll talk about petabyte scale. You don't really hear terabyte scale anymore because that's relatively common in terms of hard drive space and that. And then exabyte and zettabyte. Zettabyte is where they're talking about by 2025, there will be between 35 and 45 zettabytes of electronic data just all over the world. Unless you're Google or Facebook or YouTube trying to archive that, you probably will not deal with a zettabyte, at least right now. I mean, computers will never need more than 640K of RAM, as was famously said a long time ago. And this is the data growth rate. You can see it's definitely not a linear growth as the amount of global data increases. Again, this is data for the entire world. Your average company will see a fraction of this. But the thing that these two charts show you is big data is very much almost an arms race between how much RAM the computers have and how much hard drive space they have and how big the data is. So you can definitely see the growth of hard drives, the growth of, although who does it look like is winning that particular race? The data is definitely growing faster than the hard drives, the individual hard drives can store. So what is really, so this continuing sliding window of big data. You can see this was my, aging myself here for sure, but my first computer was a Commodore 64. For a Commodore 64, 65 kilobytes is big data because it won't fit in the computer's RAM, and you can only fit about 3 of those on its floppy drive. So dealing with any data set that was bigger than that was a challenge, not that any of this existed back then. The IBM PC 641K would be that because it had 640K of usable memory on it. Later on, they got to, you could have an entire megabyte of address space, but you had to share that with the operating system in your program, and then that space above 640K, you had to bank that back and forth with your additional RAM. So I don't know, I kind of count that as the first time I dealt with big data because I had to write a program back in the day that would use a large amount of RAM, and you had to do all kinds of stuff to get that memory in and out. So really the threshold of big data is where you're before it, it's easy to deal with, but now you cross this threshold and it's hard. And right now, the threshold for that, you can get 64 gigabytes on a common motherboard that you can buy on Amazon.com. If you're willing to spend a lot more money, I've seen them as high as 100 gigabytes. They might be higher. I mean, the 64-bit processors can address quite a bit more than that. And the biggest hard drive that I found right now is 6 terabytes. But I'm sure in specialty cases you can get bigger than that, or If not, you will soon. So what are some common sources of big data? Activity-generated data, that's one of the biggest ones. And that's one of the ones where companies will run into this before potentially some of these other ones. So one of the original sources of big data was these log files that are stored on websites. So Maryville University has a website, and there's all sorts of people clicking on things, and all this is going into a access log, because most of the web servers, they create a very standard access log. It tells you what IP address it came from, what they did. For a while, companies mainly considered this just data to look at if something went wrong. But then later they realized this is really useful data. We can tell what is the most common page on Maryville that users exit from. So they're clicking along, looking at things, and I don't know, some page bores them to death and they leave. So that is one of many, many, many statistics that they want to look at. But this is this huge amount of data that they have to go through, because these will run for months and months. And just imagine a top 100 website like an Amazon or a Google. I mean, the amount of logged data that they have is just staggering. But it's very useful information. So that was one of the first sources of big data. Then, of course, financial markets. You deal with ticks coming in irregularly, literally every second. You'll deal with bars and other ways that that's abstracted. Then legacy documents, so old documentation in the company. You want to be able to search through it. This is Google's. This is what Google does. They need to be able to search through large documents. Social network profiles, that's a big one. The insurance industry is somewhat interested in that in terms of what can we tell about people from social media. Of course, everybody's interested in looking at social media. That's a big topic. Software as a service, and like I said, website access logs. So as you're using these phones, websites, all this stuff, the first and last one, you're just generating lots of data that companies will want to look at and use for different things. So just to give you some of the vocabulary, if you learn nothing else from this talk, you'll learn some of the top vocabulary in this. You'll often hear of the 3 V's of big data. It's definitely something to remember. That's mentioned a lot in big data. We'll get more into that. Data stream processing, very important and very interesting topic of big data. That's probably the area that I deal with it the most in terms of big data. Out of core processing, another important term. We'll see what that means. And then we'll look at just how this is actually done. There's the Hadoop distributed file system. You've probably heard of Hadoop. That's frequently associated with big data. And then Spark is another approach to that. MapReduce, and then that last one, that's how Spark does it. So Hadoop and Spark are kind of the 2 big names in this. So the 3 V's of big data. This talks about characteristics of data that makes it hard to deal with. So the first V is volume, and that's the one that most people think of. You've just got a lot of data. You've got a punishingly big data set. And often what you want to do on the big data set is not necessarily that difficult. You might just want to calculate the mean, mode, or some other statistic on it, but it's over 100 million records or something like that. So it's often you'll want to do a very simple algorithm, but just the fact that the data is so big, that's the problem. The other 2, velocity and variety, you don't tend to think of as much. Variety is relatively obvious. It just means that in these large data sets, the data may come from different sources. You may want to look at social media networks. Well, there's a lot of social media. There's LinkedIn, there's Facebook, there's all sorts of them. They're all different data sets. They all have different characteristics, but you need to bring them together and aggregate them and use them together. So variety can definitely be a challenge, especially when it's so big that physically putting these data sets together may exceed what storage capabilities you have. And then velocity, that's a really interesting one. That's one I've dealt with to some degree. Velocity has to do with the data is constantly changing. So the way you deal with that one is one very important problem that the U.S. Census Bureau had was, they take the census every 10 years. They were doing this by hand. It took longer than, it was taking longer than 10 years to do that. So that's an inherent problem. That's when they really started to invest in computers. But consider the currency markets, which is used by banks and companies all over the world for arbitrage to move money from euros to dollars and all that. It's not like the stock market. It's constantly going. It stops at certain periods, but it's just the stream of data that goes on and on and on. Even stocks, the bid-ask spreads and all of that is just constantly coming in. So if you want to calculate the average price of a stock, you have to decide over what time or how do you do these running statistics on it. So that is where velocity becomes very important. So the data is changing rapidly under you. And that's the 3 V's, just volume, velocity, variety. Volume, you're dealing with lots of records. Velocity, you're making determinations of, are you doing this batch mode, or are you... A lot of times you're just dealing batch mode and the data is not changing literally right out from underneath you. That makes it somewhat more complicated. And then variety. Are you dealing with structured data? Structured data is something that looks like it came from Excel. It's rows and columns. Unstructured data is hierarchical and a lot more complicated to deal with. All the way up to just text. So streaming data. This is another big topic in big data. This has to do with with velocity. So you deal with data streams where the data is just constantly coming in. One thing that I looked at, and I did a presentation on it, I guess about a year ago, was how many of you have ever heard of Kickstarter? Okay, social media, you have an idea, you want to make 1,000 widgets, but it costs money to make the 1,000 widgets. You need that money before you sell it, so you just put your idea up on Kickstarter and it goes. Some of these Kickstarters make insane amounts of money, like multi-millions of dollars, and it's very much real time. They run for about 30 days, people pledge, the number goes up, and it's a very interesting process. So I use Kickstarter for each of those 3 books has had a Kickstarter campaign that goes with it. Naturally, I'm looking at Kickstarter, so I want to apply data science to it. Why would I not? What makes a successful campaign? So what I did was write a program that analyzed Kickstarter programs as they're going, and try to look for what makes them successful. What kind of a social media splash are they making? How are their pledges coming in? But the point is, this is variety. I've got all kinds of data coming in. I've got tweets coming in. I've got Facebook postings. I'm using Google to just find new web pages, blogs that are mentioning these products. I've got velocity because I'm analyzing the Kickstarter program in real time. I can't just go download it later and batch it because the data doesn't exist at that point. I'm literally using an automated program and hitting their website and seeing these products go up. So that's an example of a project that I used that used all 3 of those. And I was also dealing somewhat with big data because I had pulled down the entire amount of data that I was using Wikipedia. You can actually download Wikipedia completely as a file and export it and use that. So I was using that to track some of the word concentrations in their descriptions. So just looking at that. Let's see. So streaming data in the real world, you deal with computer network traffic. That's used a lot in security. That's a project I'm looking at right now with part of my doctoral research. Is they're looking literally at network intrusions of security, seeing data coming in and trying to assess threats in real time. Phone conversations, believe it or not, it's analyzed not even just to eavesdrop, but just to determine network capacity, and because the cell phone networks can degrade and go up as bandwidth is available. So they literally monitor that stuff in real time to determine how well the network is performing. Web searches, and then sensor data. Sensor data is becoming a big one. A lot of these companies have sensors all throughout their building to monitor the HVAC systems. And these will generate a lot of data because you've got 1,000 or 2 sensors throughout a decent-sized corporate building, and they're all just streaming in all sorts of data, and you've got to sync them all up and make sure that you're doing the right time slice across them all. So there's challenges there. So that's streaming data. We hear about streams a lot in big data. And then the real issue with streams of data is there's no beginning, there's no end, and they just go on forever. So a lot of things, when you want to calculate some statistic on a data set, you usually pick a defined begin and a defined end. But streaming, you really got to just keep going as the data comes. And you can't, in traditional data, batch processing, you can just, if you think about how you calculate a standard deviation over a typical data set, you find out how many items are in that data set, and there's 2 passes. You've got to calculate the mean, so what's the average of that data set, and then you kind of go back to the beginning and you loop over it again, and you calculate the average deviation of each of those items from that mean. Well, in streaming, you can't do that because it's drinking from the fire hose. The data is coming at you, and you need to deal with it in a single pass. And there are various algorithms for things like standard deviation where you can actually do it in one pass. The math is more complicated than your classical version of that. And then another thing you'll often do with streaming is you just realize that you won't be able to calculate this number exactly correct. Statisticians are usually pretty used to this because you've got the confidence intervals, but it's that sort of thing. So, like the chart that I show you there, this is one area of, I have an open source product called Incog. It's not just me, it's a number of people have contributed to it, but I know a lot of the questions are around people who do real-time currency trading with this. They use these programs called NinjaTrader and MetaTrade that just literally sit there and they're hooked to a live feed with real money, and they look for patterns in the data, and they're actually executing programs, and it will execute real trades with real money, with your money, and do that. I don't actually do this myself, but I do answer questions for them. So it's kind of an interesting, I'm just not into it enough to do that with real money. I would probably use a lot. Yes?
How do you determine how successful those are if multiple people are doing it and everyone's looking for that?
Well, what's really tricky about that is a lot of people, they call it back testing. So you will test this on pre-recorded data. And they have a big competition every year. It is from MetaTrader, and they see who can make the best algorithm to generate the most amount of money. And there's a student from Russia, I believe, last year. It's usually somebody from Russia that wins it, at least the last few years. And MetaTrader is actually in Russia. But they asked him, I forget what the prize is, but they did ask him, are you going to unleash this algorithm on the world and bring the exchanges to a halt? And he said, no, I would lose a lot of money. Because backtesting, the big difference is backtesting tends to assume that whenever you place a trade, it will be executed immediately and at the price that the bid-ask spread said that you could get it at. The reality of when you're actually trading these, that's the part that is really hard to test, because you can't necessarily tell the volatility that's going to be present at that point, and you may or may not get it at the value. And often, this is high-frequency trading, so you're going in and out very fast. So if it's just pennies different on your ask, you're potentially in trouble. So that's very challenging to look at. And this also shows, too, a good, you might have seen that. That's a candlestick plot that's used a lot in finance. They're looking for patterns on those. Basically, it's just showing the high and the low and the second and third quantiles that those prices achieve. But that is, what's good about that is actually taking a lot of data and putting it into a consistent form. Underneath that is a whole bunch of individual trades coming in, and whatever size those bars are, be they minutes or hours or days or even years, you're just averaging those all together. And that's often a way that you deal with big data, is you average it down into some meaningful number. So imagine those bars are years. Well, really, there's all sorts of transactions coming in, maybe even at the same time, seconds apart. So that's another common way to deal with big data. Okay, out-of-core processing. Now, my background is primarily in computer science, so this is one that particularly interests me. I'm very interested in the algorithms of big data and how do you make this stuff efficient, because I've seen that many times. The first, Donald Knuth, who's sort of the father of computer science, one of his most famous quotes, I'm paraphrasing, but is premature optimization is the root of all evil, or at least close to it. First order of business is get the program to run accurately. Next order of business is to get it to run fast. So that to me is very interesting, because I'll show you some examples of this where just small changes can mean a whole lot on dealing with big chunks of data. And usually when you're dealing with big data, you experiment on small pieces of it, because, I don't know, it may take me 5 or 6 tries to get the program to work perfectly. Well, if that's gigantic data and it's taking 3 or 4 days to run through it, I don't want to find that out on the big data set. Sometimes you can't help it, but you can minimize that as much. So out-of-core processing is basically saying, don't write your program so that it will blow up if you run out of RAM. Most programs are written, R is a lot of very successful, popular programs are written like this. If you use R, if you use Python scikit-learn, which is another statistics package, if you load a giant data set in and it doesn't fit in RAM, it'll just stop. It'll error out. There's a real good program for this. It's got really funny names. Programmers just love to give these open source things unusual names, but this is called Vocal Wabbit. Sounds like a Bugs Bunny reference. But it does a lot of the machine learning and modeling. This thing will never run out of memory because it's using the disk to do all of this. It uses RAM to speed it up. In many ways, this is how classic software was written. You used to do everything on disk and just use the RAM as a bit of a cache because nothing would fit into RAM. So it may run forever if the algorithm doesn't scale correctly, but at least it's not going to run out of RAM and stop. So that's another very big movement in big data and programming around it, is don't just suck the whole thing into memory. Think before you do some of these things and make sure that you're only doing really what you need to do. And a lot of the Unix utilities work this way. So if you get a really, really big file, often I just want to look at it and see what's at the top of it. Well, if it's a CSV file, you might be tempted to just double-click it and open it in Excel. Well, that'll, except for the very, very latest versions of Excel, which are now becoming big data aware, that'll just blow up. But in most Unix utilities, you can just do head of the command called head, which shows you the head of the file and as many lines as you want to. Because even if a file is terabytes long, it's not a big data operation just to show you the beginning of it. Or editors. There's big data aware editors. If you just want to open the file and scroll through it, they don't need to load that whole file into memory just for you to look at it. Yet most text editors will. You try to open a notepad, it'll spin for a few minutes and then die. And this is another term you'll hear in big data a lot, and just IT sort of in general is ETL. It's just extract, transform, load. So this deals with data warehousing. A data warehouse is just nothing more than take all the data out of the active system. So say Maryville University, they've got computer systems that are tracking student registrations, adding classes, dropping classes, all this kind of thing. Well, there's another part of Maryville that wants to do reporting and analytics on this. You don't want them going into the live system and doing this. You'll extract it into a data warehouse, extract it from the main system, do any transformations that you need on it, because usually you want to simplify it in some way for the reporting, and then you load it into there. So that's ETL, just another concept you hear. So another thing, perhaps takeaway on this, is Hadoop. So Apache Hadoop is probably the poster child in terms of software to handle big data. Hadoop is one process for this. There's another very closely related one that's actually by the same people, and it is, that being Apache, it is called Spark. So if you read some of the cutting edge articles on this, they'll talk about Hadoop or Spark, who is almost as though they're in competition, that one will be, that Spark is the new up and coming one, and Spark can be 100 times faster than Hadoop. Spark is actually based on Hadoop. It uses it, so they're very much used together. Hadoop uses something called the HDFS. So what's really nice about this is, like I said, you can only buy hard drives up to 3 terabytes or so. You can use just normal everyday computers, hook them together on Ethernet, just network. You probably don't want to use Wi-Fi because it'll be too high bandwidth. And those hard drives under Hadoop, the Hadoop file system, they become one single hard drive, and you can put very large blocks of data into there. And now you have volume solved. You can load it into just commodity hardware like you could go to Walmart and buy, and you've got the data available. HDFS it can go up to 200 petabytes of storage. You can have up to 4,500 clusters on it. There's ways to go even beyond that, but this is just out of the box. And it can support up to 1 billion files and blocks. So some operating systems have limits on that. You put too many files in a directory, you'll get in trouble. But this does not have those limitations. Whoops, double-clicked. Okay, so why is big data hard? Like I said, the 3 B's, but another part of it is algorithms don't just scale up nicely all the time. So like I have here, if you have an algorithm that processes 1,000 records in 1,000 seconds, so 16 minutes, you may think that it would scale linearly, and 1 million records would take 1 million seconds, or 277 hours, which is a multi-day job that's still reasonable. Unfortunately, they don't scale up that nicely, because it's almost like a matrix. You have rows and columns. As you add more and more, it just adds on to it. So they scale up at different rates. And I have a few examples of that. So in computer science, you hear a lot about, you'll hear big O notation. So that's just a way of saying how well does an algorithm scale. And there's several different ways. They're usually written like this: O1, O log n, O(n), O log n. They look a little bit odd at first, but what they're really saying is O1, that means no matter how big the data, because n is the size of your data, so no matter how big the data is, it's going to take just the same amount of time. It'll take a minute, I don't care how, or a second, or whatever that unit of time is. That doesn't happen very often. That's really nice. I mean, if I tell you, so I'm going to give you this big list of words or numbers. If I tell you just find the first word in the list, it doesn't matter if the list is a terabyte long or a couple of bytes long. That's easy. Order log n. So that is basically something that, order n, let me explain that one first. So that's where it scales up evenly to the number of items. So find the longest word in the list. Well, no matter how long that list is, you're going to have to visit every element on that list. So that's going to scale up linearly. If 10 records take 10 seconds, 100 records is going to take 100 seconds. Sometimes it scales up less than linearly, and that's good. Order log n, that will scale up sorting. Most of the sorts are order log n, because often you can get by with not necessarily having to visit, searches. So if you need to find an item in a list, often you don't have to visit the entire list. If I tell you to find somebody's name in a phone book, you don't read through every single item in there. You actually execute one of the classic computer science algorithms called a binary search. Humans do it all the time. They just don't have a fancy name for it necessarily. But you open it up about halfway, and you realize, oh, I'm on the H's. I'm looking for something before that. So then you open it halfway, and you keep opening half and half and half until you're pretty close to it, and then you just start searching down the row or down the column. So that's these first three up to about the fourth one. Those are the really desirable ones because they're scaling pretty well. Most of the searches are in login, quick sorts and 10 sorts and those sort of things. Order n squared, that's exponential growth. That's not so good. And then there's even worse. There's factorial growth. I'll show you an example of one of those. So this is the big O chart. You see this a lot in computer science. Computer scientists like this chart almost as much as actuaries like the standard distribution chart. So this is used a lot so that you can visualize how quickly these are growing. So obviously that yellow one or the purple one, that's a bad thing. The more data you have, it just explodes. And certain algorithms are like that. So what you do with an algorithm like that, if you've got to deal with it in big data, is you either cut the data set down or you use something called a meta-heuristic, which is where you're not going to look at every single potential solution to that. You're going to accept a potentially good enough solution. And I'll show you an example of that. So you want to avoid the naive design. The naive design is if I wanted to find the name in the phone book, the naive design would just literally to start at the beginning and start reading through. And if that's the only way you know how to do it, then that's what you're stuck with. But that's why it takes further analysis to really find better solutions to your programs to allow them to do that. And if you're not a programmer, you need to select tools like Vocal, Webbit, or others of these that are capable of handling this size of data. And Apache Hadoop, that does it quite well. You can load a CSV file into this whole thing that's just gigantic. Find the meaning of it real easy. You can program, again, these comic technical names they like to use, but it's called pig, just like the animal. So that lets you literally write SQL against these giant CSV files and take means and other counts and other more complicated statistics that you want. Also, you have to deal with, is the solution good enough? You may not need an exact solution. And you need to think of this sort of in the beginning. I've dealt with many systems where the programmers initially designed it for a small set of data that they had for the test case, and it worked just fine. And you get about a year into the real programming run, and certain parts of the program just fall apart because now we're getting more and more data loaded into the system, and you run into a problem. So I'll show you an example of, a couple of examples of where you don't necessarily just want to do the naive approach. This is an algorithm. This is actually I think it used to be a common interview question with Silicon Valley software companies, because they like to just give you questions to see if you can rationally think through these things. I suspect it's not anymore because it's been mentioned like 1,000 times on the internet that this is a common Google question. But it's really not that complicated. So say you want to choose, say you have a really, really large amount of data and you want to randomly sample some set from it. And this is common. You often want to do this. This is probably the easiest way to handle big data is make it small, deal with a smaller sample of it. So you've got this large list, or maybe it's streaming, maybe it's an infinitely large list of data, and you need to find a sample set of that. So the way it's expressed often is, if you want to choose a couple of random people on Earth, well, the first problem you need to deal with is you don't know exactly how many people are on Earth. So to do this, you need to literally go out and visit every single one of them, put them in a consistent ordering, and that's the trick. You've got to have this consistent order, so you need a really large notepad that you can remember. Okay, Tom was the first guy I talked to, then there was Jill, and you've got this big long list. Eventually you're done, and I don't know, there's billion or however billion people there are on the Earth. Now you need to pick a random number between 1 and that range, or however many random numbers you want. If you want 10 people, you choose 10 random numbers. Now you've got to start all the way back again and go through the whole thing. And when you get to person number 3,436,000, whatever those random numbers were, you say, okay, you're coming with me, I've chosen you. Well, the problem is, however long it took you to do that, people have surely died and been born, and that's velocity. And most likely, the world's population, it's increasing, so barring any sort of cataclysmic event occurring, you're going to be biased towards the younger people, because whatever that range of random numbers that you picked is not inclusive of the whole set. So you need to do this kind of as you go. So doing something big more than once in big data or streaming is always bad. You try to do it just once. And the name of this algorithm, it's a very simple algorithm, but it's mentioned a lot in big data, is reservoir sampling. So the way you would do this is you would go to reservoir. The reservoir is just the list of people that you're sampling. So if you're sampling 10 people, it's going to be a list of 10. It's just a holding queue. And in this case, I'm just sampling 2 items. So so basically you're just going to handle this as you go. You're going to keep this list of the 2 items and just keep going through the list. So the first 2 is pretty easy, because if you sample 2 items from a list of 2 size, you get the list. The sample and the population are the same. But when you go to this third one, now you've got to think, okay, do I want to replace anybody in my reservoir? Well, you now have a total of 3 items, so the odds of that third one having in that sample, if you had created it, would be 1/3. So you just generate a random number, and with 1/3 probability, you will replace one of the items in your reservoir. And then there's another trick that you do too, that you make sure that you don't have to generate 2 random numbers, because you might have to generate the first one just to determine if you're going to do it, and the second one to determine which person in the reservoir is going to get replaced. Is a term you hear a lot in statistics, and this too is bias. You don't want to accidentally tip the scale so that you're going to more often choose something. And then you keep doing that. So this is graphically how you do it. Item number 1 comes in, it goes right into the reservoir. Item number 2 comes in, it goes right into the reservoir. Item number 3, we generate a random number in a form with 1/3 probability. Well, 3 didn't make the cut, so he doesn't go in. And then we put 4 in also with 1/4 probability, and it does come in, so he goes into there. So it's a random process because you're randomly sampling these. So you want to try to pick these as randomly as possible when you're doing that. And you always want to randomize your list. Like a classic data set that's used in statistics a lot is Fisher's Iris flower database. So he's got 4 columns that describe 4 different measurements that you take on an iris flower, and then there's 3 different irises and 150 rows in the whole database, 50 from each flower. And the idea is you build a model so that you can predict which species of iris this is based on those 4 measurements. But that data set, as you download it, is sorted by iris flower. So the first 50, then the next 50. So that would be a disaster if you decided to, say you decided to set aside 50 of those to validate your model at the end, and you just took the first 100, you'd chop off the last flower. So randomizing your list is very important. That's why there's all sorts of algorithms to do that. So algorithm design, you always examine the brute force approach, but you don't necessarily use it. And another I won't get into it too much, but it's very common in computer science, dynamic programming, not to be confused with dynamic programming language, is an entirely different thing, but it's break it up, divide and conquer, break the problem up into smaller groups and solve those. Dynamic programming will always give you an exact answer, whereas the best answer, whereas meta-heuristics give you an acceptably good answer. So dynamic programming, those can take a while to execute. So there's a comic strip that's very popular with math and science people called XKCD. You may have heard of them. I see heads nodding. They're pretty cool. I particularly like this one because there is a very common problem in computer science called the Traveling Salesman problem, where this guy, the traveling salesman, needs to visit maybe 50 different cities. What's the shortest route between them? This sounds deceptively simple. It's really hard to write a program to solve this in any reasonable amount of time. So the brute force solution, n factorial. N factorial gets big fast. So the solution to just brute forcing, trying every single path through those cities is order n factorial. So with 7 cities, that's about the most that a calculator can even tell you, because that is going to be 10 to the 100th. And I think there's only something like 10 to the 23rd atoms in the known universe. So that's prohibitively hard. Dynamic programming can get that down. That's still a big number, potentially, for the numbers of cities, because you've got n squared and then 2 to the power of n. That gets big in a big hurry. Of course, the joke is, or you just go on eBay and sell it for the traveling salesman, and it's order 1. It's the easy one. So the Traveling Salesman, there are all sorts of meta-heuristics for solving this, genetic algorithms. One that I particularly like is simulated annealing. There's many others, but this one's pretty easy, and it's amazing how quickly it will do that. So this is 500 cities. So that's 500 factorial. That's a big, crazy number. So that's if you wanted to try every combination through those cities. We humans can eyeball that, and we can say, okay, that looks reasonable. I don't see them doing anything overly stupid in terms of just going over there and then coming back and doing that sort of thing. So that's using simulated annealing. That's a meta-heuristic. So I'm just telling it that I would like a reasonably good solution. And it can find, I ran this and found it in probably about 15 minutes, just using a JavaScript program. So I can actually show you this one. It's a example that I have on my website for some of the books, and basically you can put the cities there. And by the way, a really good way to test the Traveling Salesman is because you need a way to know what truly the most optimal solution is. The way to do that is put the cities in a circle. If you put the cities in a circle, then you can eyeball it. It better be doing the perimeter of the circle and not cutting through. So with just 50 cities, although 50 factorial is pretty darn big, but you can run it, and it's a Monte Carlo type situation, and it very quickly finds that. And then once it stabilizes, it doesn't change it. So just eyeballing it, that looks like a pretty reasonable set. You could also do it, I'm not going to let this run to completion, obviously, but cities 500, and that doesn't matter. So now it starts with a random, so it's just all over the place. Now a way that you can tell, just eyeballing these, if it's a good solution or a bad solution, is how much black do you see. You should not see that much black, because black is from those paths just overlaying each other. But you can start it up, and you see the black starting to dissipate. And that is it, basically just randomly. Basically, a simulated annealing works by, there's something called a random walk, which is where I would just randomly try different paths, and I would keep track of what one is the best. The problem with that is it'll take a really long time to do that. Then the next one is hill climbing. That's where you step through these. It would be like if you wanted to try to find the highest point on Maryville's campus. You would basically look around and you would say, okay, which direction can I take a step that will take me one higher? Well, the problem is I would be in a local minima or a local optima right now because I can't see any step that I can take within my span of walking that will take me higher. So I would be stuck here. I would look around and say, yeah, I'm done. Simulated annealing means that sometimes you'll take a lesser step so that you can, and there's a whole way that you schedule that, and it's based on metals cooling, but the degree that you allow that basically decreases as you get closer. So the amount that this thing accepts an inferior solution decreases as it goes. So you can see it's gradually getting better, but and you can see the length there is decreasing. And if you let this go long enough, it will eventually settle where it'll stop. And that's an important thing with meta-heuristics. How do you know when you're done? You know you're done when the solution has not improved for some specific amount of time, or the path is short enough. You can put in a number and say, okay, once you hit this, I'm good with that. But that is very much big data. That's generated data, but it's going through lots and lots. So you can use these type of searches on big data sets so that you don't have to do the entire thing. Is it good enough? So just to explain sort of my sphere, because there's people who are really, really into big data who are hired as experts. They know how many computers to put on a rack, how to arrange the racks, all that kind of stuff. I don't tend to get into the low-level plumbing of it. I get into the algorithm design and using the infrastructure to handle the big data. So data scientist is a very sort of new term for people who do this sort of thing. Data science is multidisciplinary. It encompasses all of those fields. Of course, how would a statistician or a math person describe their own field? They'd use a Venn diagram. So this is a Venn diagram that describes data science. So hacking skills, math and statistics knowledge, and substantive expertise. And these are all very important things, because often the first battle that we deal with at RGA with these data sources is often we will get data from filter the sticky files, and okay, are they comma separated or are they tab separated? That's two different values. Do they have a header? Do they not? That's another two. Well, that's four different permutations. Yeah, they give me a file and literally each of those four combinations. So data wrangling is what you call it, but you spend a lot of time just getting the data in a reasonable set. Math and stats knowledge, very important. Substantive expertise, that is, do people know anything about the data at all? So we use that a lot. At a company like RGA, that position, or that part of this knowledge set would be underwriters, actuaries, accountants, those professions. And this is often describing a team, not just one person. So my contribution on this, I'm strongest on the hacking skills. I mean, a computer science background. Math and statistics knowledge, I've done a decent amount of that. Substantive expertise, yeah, I know. I mean, I've been in the insurance industry a while. I am not an actuary or an underwriter, so that's where we get other people involved. But all three of these are very important. And if you take the substantive expertise out of there, you have machine learning. And that's where you are literally just looking at the data, trying to find patterns without even knowing what it means. How many of you have ever heard of a website or competition called Kaggle? Okay, yes, some of you. Kaggle is competitive data science. So right now, they have a competition running on March Madness. You've probably seen where you try to predict which team is going to win through the whole basketball tournament. Well, Kaggle often does strictly machine learning. They had one on the Higgs boson not too long ago where you tried to predict which particles were the God particle. Do you need to be a physicist to enter this? No, you just need to know how to analyze data. And sometimes they have the data so redacted or anonymatized that you don't even necessarily know what you're looking at. So it's a competition, and you can win $100,000 sometimes in some of these competitions. Usually the $100,000 or so that you win is just the side prize to the fact that you get hired by Google the next day. So that's another part of this. And then if you're just looking for some software to deal with this, there are distributions. Both of these are free. I really like their model. You can download their software and install it. And then if you want consulting services, they are there to charge you for that. But their software is completely open source. They're both based on Hadoop and Spark. So you can download it's called a virtual machine image, and it's not too hard to set up at all, and then you're immediately there and playing. Hortonworks has that one. And you're immediately there and playing with the Hadoop environment. That is it. Are there any questions? Yes?
I guess in relation to our major, how close do data scientists work with actuaries?
Do you want to take that one?
Actuary, he's a data science. We work together.
Yes. So the skill set for actuary, and I asked Dave because he is heavily involved with the Society of Actuaries in one initiative that they have called the Cultivate Opportunities. So there's a lot of overlap between data science and the traditional actuarial. There's also a number of other things that actuaries do that I don't understand at all that's outside of data science. But yeah, you've got a lot. I mean, you've got the probability skills and the statistics skills, so it puts you in a good spot to potentially get into the field of data science.
Yeah, the society recognizes the opportunities in data science, and the future syllabus will reflect some of that, trying to train actuaries to be better able to move into non-traditional areas beyond just insurance companies.
Yes?
Given large data, how do you ensure quality of the data and avoid overfitting, that is, your model describing the noises rather than their correlation?
Overfitting is always difficult. It's particularly difficult with big data. So with the random sampling, there's a technique that is used a lot in the Kaggle competitions. It's called cross-validation, which is where you take your data, it's called k-fold cross-validation. So you take your data set, randomize it, very important, and then you break it into, say, 5 groups, and you use, so that 5 groups, if you leave one of those 5 partitions out and use the other 4, that means that there are 5 different combinations of that data that you can use. So you now take the model and so if you use that as one big group and you try to use it on Kaggle, so you took that one piece of data and you built your model on it and then you validated it and looked at your score, you'd be like, wow, I'm going to go work for Google when this is done. So, but that's overfitting. Your program has essentially memorized the data, so what you've got to do is you go through those 5 cycles, you train it on 4, you validate it on the one that's left out, and you see how, you basically see how close you are. And your score on that left out validation one is usually relatively indicative of the score you're going to get on Kaggle, because that's all Kaggle did, is you're not sending your program to them, you're just filling out your predictions on their data that they gave you, and they held some data back from the data set to evaluate. So there's a lot. Minimizing the effect of overfitting is a huge area. There's all sorts of ways. Cross-validation is one of the most common. Yes?
Where do you see the field of data science going in the future? It seems like a lot of companies use it for marketing, insurance companies, but what's next?
Well, there's a lot of ways that it can be applied. So you see a lot of information. There was an article out by Swiss Re not that long ago that talked about potentially, the way we underwrite right now is we ask for all kinds of information from the policyholders. The wearables, I don't have it on right now, but I have one of a Fitbit. So these type of things, as you do more and more, if you get more and more data available, you can try to correlate that, hopefully causate that, to actual mortality predictions. Google is actively working on, I guess the people who work at Google, they've made so much money, more money than you can spend in a lifetime. So what's the next goal? Oh, have multiple lifetimes. That would be even better. So they're working on, and how do you extend the human lifespan? Well, first you've got to take out the quick kills like strokes and heart attack, so there's a lot of research looking at just non-invasive data that you can collect on people, because obviously you can cut into the person's leg and send a probe all the way up to look at some of the main arteries going into the heart, but who wants to do that on a daily basis? So if there's other ways that they can correlate enough data and just find these other biometric indicators that let you know you're 24 hours or so from such an event, that could help with that. And then they're also just looking at, so that I could see that one potentially being useful to the insurance industry. But there's all sorts of other ways that they are looking at this sort of thing. Thank you.
Yeah. Thank you, Jeff. Really like, if you have more questions you want to discuss with Jeff, you may do after the section.
Oh, okay. Well, thank you. Appreciate it.